Have you ever wondered how we really know if more education leads to a higher income? Or, what things actually predict how long someone might live? Well, today, we are cracking the code on one of the most powerful tools out there for answering exactly these kinds of questions. Think of this as your guide to understanding the big picture of linear regression before you even crack open the textbook. So, our investigation starts right now. The world is a pretty messy place. It's just full of data and noise and a million things happening all at once. So how do we find the real signal in all that noise? How do we find the actual pattern that connects one thing to another? That's the huge puzzle we're tackling. And our main tool for the job? It's linear regression. At its very heart, linear regression is all about finding this red line. See all those blue dots? Each one is a person, showing how much money they have and how many problems they have. You can kind of see a general trend, right? Well, the magic of regression is that it uses math to calculate the one single best-fitting line that sums up this entire relationship as perfectly as possible. Okay, so to really get how that line gets drawn, we need to look at its blueprint. And don't worry, it's way simpler than it looks. Once you get this, you'll understand the logic behind pretty much every regression output you'll ever see. Yep, this is it. This is the engine that drives linear regression. Everything we're about to talk about comes right back to this simple little formula. I know, it looks like something from high school algebra, and that's because it is. But this simple engine lets us make incredibly powerful predictions about the social world. So let's break it down piece by piece. First up is why. This is our outcome. It's the thing we're trying to understand or predict. In our last example, it was the number of problems. Basically, it's the variable we're trying to find an answer for. Next, we've got A, which you'll almost always see called the constant. Just think of it as the baseline value. It's the predicted value of y when our other variable, x, is 0. So in our money and problems example, it would be the number of problems someone has with $0. It's where that red line starts its journey on the graph. And that brings us to B, the slope. Okay, this is the crucial part. This is usually what social scientists care about the most. It tells us the direction and the strength of the relationship. For every $1 increase in money, how many more problems do we predict? That number, that's the slope. All right, that's enough theory. Let's put on our sociological detective hats and apply these tools to a real-world case, using actual data from the General Social Survey. So here's our research question. It's a classic one. Does getting more education actually influence when people start having kids? So, our dependent variable, our y, is the age someone has their first child, and our independent variable, our x, is the number of years of school they completed. Let's see what the data has to say. Okay, here it is, our first piece of evidence, the raw output from the stats software. And I know, it looks intimidating. It's just a wall of numbers, but don't worry about it. Now that we know the blueprint, y equals a plus b of x, we can ignore almost all of this and just zoom in on the few numbers that actually tell the story. So the really cool part is translating these numbers into a story. The slope, our b, is 0.76. What does that mean? It means for every single extra year of school a person gets, their predicted age when they have their first kid goes up by about 3/4 of a year. Pretty interesting, right? And then look at this adjusted r-squared. Think of this as a score for our explanation. It tells us that education all by itself explains about 12% of the story. Now, that's not bad for just one variable, but it also tells us that 88% of the story is still a mystery, caused by all sorts of other factors. Life is rarely simple, and social outcomes almost never have just one single cause. So any good detective knows you have to bring in other suspects. Let's add a second variable to our investigation, the number of siblings a person has. And just like that, we've leveled up. By adding a second independent variable, we've gone from a simple analysis to what's called a multivariate one. And this is so important because now we can see the effect of education while also accounting for the effect of siblings. You're officially in the big leagues now. Here's our new evidence file. See that? We've got a second line now for number of brothers and sisters. Our model is getting more sophisticated, which means our ability to tell a more detailed story is getting a whole lot better. Let's see what these new clues tell us. So now we have two effects going on, but how do we know which one's more important? Well, we can't just compare the slopes we saw, because 1 year of school is a totally different unit than one sibling. It's like comparing apples and oranges. So to solve this, we look at a standardized number called beta. Beta puts everything on the same scale, so we can finally compare them side by side. And as you can see, education with a beta of 0.33 has a much, much stronger effect than the number of siblings, which is way down at negative 0.07. But wait a minute, what if we've been missing a huge piece of the puzzle? What if this relationship we've been looking at doesn't actually apply to everyone in our sample in the same way? A really great final step in any investigation is to check if the story changes for different groups of people. So, let's split our data and run the exact same analysis twice, once for just the males and once for just the females. This is called a stratified model. And just by glancing at the two outputs here, you can already see the numbers are different. The story is not the same for men and women. Let's break down what this twist actually means. This table makes the twist totally clear. The effect of education is stronger for females, a slope of 0.79, than for males, at 0.67. But look at that adjusted R-squared. For men, our variables explain about 10% of the outcome. But for women, it's 19%. That is almost double. Our model is a much, much better explanation for when women have their first child than it is for men. So there you have it. We went from a simple line on a graph to a pretty complex story with a surprising twist at the end. Before you go off and start your own investigations, let's do a quick recap of our process and go over a few critical warnings from the detective's field guide.
Always remember this logical flow. It's such a powerful way to build knowledge. You start simple, then you add complexity, layer by layer, and then you check to see if the story is different for different groups. This is the why behind the process. It's how you build a really solid, nuanced argument using data.
And finally, every detective needs to know the rules of the road. First, regression only looks at complete cases, which means anyone with missing data on any of your variables gets dropped completely. Second, watch out for something called multicollinearity. It's a fancy word, but it just means don't use two variables that are basically measuring the exact same thing, like income in dollars and annual salary. It just confuses the model. And third, remember this whole thing assumes the relationship is a straight line, so it's not the best tool for patterns that have big curves in them. Knowing the limits of your tool is just as important as knowing how to use it. So we've seen how linear regression can untangle this really complex web between education, family size, gender, and one of the biggest decisions in life. It takes messy data and turns it into a clear story. So the final question is for you. Now that you've got the blueprint, what puzzle about our social world would you want to solve?